Carbon capture has a fundamental physics problem, and it's a problem that can be understood by using trail mix, but more about that in a second. First, some context. Carbon capture is a technology that does exactly what its name implies. It captures planet-warming carbon, like carbon dioxide, takes it out of the atmosphere and stores it somewhere like underground where it won't cause climate change. I mean, it sounds like a very promising premise. This technology could not just stop climate change, but even reverse it. It also sounds like a fairly good compromise. This technology could turn pollution-heavy sectors like power generation or chemicals into much more climate-friendly alternatives. No need to build out brand new, expensive, green, renewable infrastructure, just retrofit what we already have. Sounds great, right? Well, unfortunately, it isn't that easy, because if it were that easy, we would have done it already. So why haven't we? What's the problem with carbon capture? Well, to answer that question, we have to cover three main topics. Firstly, what actually is carbon capture, so we can learn the different types and how they fit into the bigger picture of climate change. Secondly, we can cover how these machines actually work, and then finally cover why trail mix is the perfect analogy for the physics problem that is going to hold carbon capture back. By the way, I'm going to be using carbon dioxide, and CO2 throughout this video, but for the purposes of this video, those are all going to mean roughly the same thing. Well, we have a lot to cover, so let's jump right in. Alright, so what actually is carbon capture? Well, it's an umbrella term for many different types of technologies that all basically do the same thing. They take carbon out of the atmosphere and store it somewhere else, but they all do it in slightly different ways. I'm going to ignore nature-based solutions here, like planting trees. That's gonna be for a separate video. I am specifically focusing on these machine-looking things. And these machines can be categorized by very unhelpful acronyms like DAC, or BECCS, or CCS, or CCUS. Now, to help everyone understand what these different acronyms mean, I'm gonna use the soulful lyrics of Cotton Eye Joe. Now, hopefully that doesn't trigger any copyright, or I'm gonna have to sing over top of that, and no one's gonna be happy about that. But more or less, that is all you need to consider when thinking about carbon capture. Where does it come from, and where does it go? Let's start with DAC, or direct air capture. These are basically massive machines that suck in normal ambient air, right, the same stuff we breathe, captures that carbon dioxide from that air, and then stores it underground. So if it came from the atmosphere and ends up underground, we could consider this carbon negative because it's actually taking pollution out of the atmosphere. Unfortunately, that's all they really do. They're not necessarily selling anything, so these machines aren't necessarily money makers. The other carbon negative technology is BECCS, or bioenergy carbon capture and storage. These machines burn organic material like trees and hook up a carbon capture system to the carbon-rich exhaust. It then captures that CO2 and puts it underground. So if this carbon came from plants, but the plants already did the photosynthesis to take it from the atmosphere, then it too came from the atmosphere and ended up underground. So it's also carbon negative. This has an advantage over direct air capture because these facilities actually produce something useful, like heat, to create electricity. Then you have CCS, or carbon capture and storage. This is similar to BECCS, but instead of bioenergy, it's attached to things like fossil fuel plants. And because coal and natural gas come from deep underground, and this carbon capture puts it back underground, this could, at best, only really cancel out or be carbon neutral. Then you have CCUS, or carbon capture utilization and storage. which is the same thing as CCS, but after capturing that carbon dioxide, you can use it for things like enhanced oil recovery. Yup, turns out if you inject carbon dioxide underground where you're also mining for oil, it can actually help get more oil out of the ground. And if that sounds counterproductive to you, you are absolutely right. But that's it. Those are the main types of carbon capture, ranging from good for the climate but bad for the economics, like direct air capture, or poor for the climate but good for money, like carbon capture utilization and storage. And now that we've established the different types and how they fit into the larger climate change picture, let's dive a little bit deeper to figure out how these machines actually work. I guess the word capture is a little vague, but it does explain a relatively simple process. Let's look at carbon capture and storage of a gas-fired power plant for an example. This plant burns gas to create the heat needed to generate electricity, and normally just exhausts the waste products, which includes carbon dioxide, into the atmosphere. A CCS system would essentially attach to that exhaust, and within that system would have a solution like amines or any other compound that actually binds to that carbon dioxide. Those bound amines then move to a separate container where they are reheated, allowing that carbon dioxide to separate. That CO2 can then be compressed and moved underground, and what makes this really smart is that the solution, the amines, can be recycled back into the main container to capture even more CO2, and the process just kind of repeats. So it's basically a closed loop system where all you need is energy, but that's kind of the problem. You need energy, and the amount of energy you need depends on how concentrated that CO2 is. Using our same example, the exhaust of a power plant, that exhaust is typically between 5 and 15% carbon dioxide. So these carbon capture systems have a relatively high amount of carbon dioxide available to them. Ambient air, right, the same stuff we breathe in, is very much less concentrated at 0.04%. So direct air capture would have to try much harder to get similar amounts of carbon dioxide. And this is where our trail mix analogy comes in. So to understand why concentration matters, we're going to use this analogy, right? If you've ever had trail mix, you'll know what you truly want is these delicious M&Ms. And in this analogy, these M&Ms are going to be our carbon dioxide molecules. If you're greedy like me and you only take M&Ms out of the bag, you find that they become less concentrated, right? Same amount of nuts, less M&Ms. You may have also noticed that the less M&Ms there are, the longer it takes to find them until you get to the very last one, which seemingly takes forever. This time can also be interpreted as energy, right? It takes a lot more energy to find M&Ms in a bag that's full of nuts than it would be to find them in a bag that's just pure M&Ms. So if we plot this on a graph, we can see that the less concentrated the M&Ms are, the more energy it takes to pick them out. Converting this back to our planet warming carbon dioxide, we have the exact same problem. The less concentrated the carbon dioxide is, the more energy it will take to capture. And unfortunately for us, energy isn't free. If you've ever had to pay an electricity or gas bill, you know this very well. So if we look at direct air capture, which like we stated is capturing carbon dioxide from ambient air, which is very dilute at like 0.04%, we can see that it takes a relatively high amount of energy and therefore money to capture. In fact, on average, direct air capture costs about $225 USD per ton of carbon dioxide. To put this in context, the average North American produces roughly 15 tons of carbon dioxide every year. So it would cost every person more than $3,000 to capture their carbon footprint. So this is not cheap at all. Direct air capture, however, is of course the most inefficient because it's the least concentrated. CCS, on the other hand, when you attach it to a very carbon dioxide rich exhaust, like a power or chemical plant, can really bring down those costs. In fact, I pulled this data from the International Energy Agency, and you can see that carbon capture gets much cheaper the more concentrated the gas becomes. This doesn't necessarily mean that CCS is the better option, because there's two things we need to remember. First, we need to remember Cotton Eye Joe. CCS is at most carbon neutral because it is neither adding or removing carbon dioxide from the atmosphere, unlike direct air capture, which can be carbon negative and could reverse climate change. And second, while CCS is cheaper per ton of CO2, it's not actually cheap because CCS is an additional cost to most facilities. Let's again look at a gas-fired power plant. A typical plant can produce electricity for about $75 every megawatt hour. And a megawatt hour is roughly the electricity consumption of a normal household every month. That same facility with CCS attached could see those costs climb to about $130 per megawatt hour. This price increase is for a couple of reasons, like material and construction costs, but one of the main issues is the quote, energy penalty. Remember, carbon capture needs energy to work. So it quite literally siphons off energy that the plant would need to, for example, make electricity, making the whole system less efficient. And when you compare it to solar, which produces carbon-free electricity from the rip at like $60 per megawatt hour, you can see that CCS is not actually cheap. It's just cheap when compared to the very expensive direct air capture. All right, I've laid out a couple problems, so let's take a step back and look at this from a broad point of view. While carbon capture is not ready to scale just yet, it is slowly getting better. The hottest and most important research area right now is finding different methods and chemistries that would lower the energy requirements for these carbon capture systems to hopefully bring down those costs. And while this innovation is great, and I applaud it, we do have to consider this concentration, or what I call the trail mix problem, right? This concentration issue means that there is going to be a physical floor to how cheap this technology can actually get, because it is physically impossible to bring the energy efficiency below this line. Realistically speaking, unless the cost of energy drops by an insane degree, which I don't see happening anytime soon, the cost of direct air capture is unlikely to go under $100 per ton of CO2, which would still cost people thousands of dollars a year. CCS, on the other hand, could get as cheap as $30 per ton for, for example, coal or natural gas power plants. And that may sound more reasonable, but again, it's still so much more expensive than just building out cheap, reliable, renewable infrastructure. Now, this is not to say that carbon capture is a false solution or amounts to greenwashing. We are actually going to need it to a certain extent. Solar panels, wind farms, EVs, these are all great, but there are many sectors where decarbonization is going to be much more difficult, like aviation or concrete. And for these sectors, it may actually make a lot more sense just to invest in carbon capture to fill that gap. Additionally, in the future, once we have decarbonized our entire economies, we'll eventually have to think about pulling all of that extra CO2 out of the atmosphere. Because all of this pollution we've already added isn't gonna go away unless we actively remove it, which direct air capture could do for us. We will just have to do it for the right price, which it currently can't do. But if you want to learn about the costs and the feasibility of other climate change solutions, make sure to check out my 10 minutes or less series where I explain different solutions to climate change, how much they cost, and how likely they are to scale. The most recent video being on nuclear, which you can watch by clicking either here or up here. I always forget. Anyways, if you've enjoyed this video, please subscribe, like, and comment. It helps a lot and it's no cost to you. This has been Carbon Anonymous, and thank you for stopping by.